Hi, everyone, and welcome to the first Eurographic Symposium on Rendering 2020 session on denoising and filtering.
I'm Jacob Munkberg, and I'm here to present our work entitled Neural Denoising with Layer Embeddings. This is joint work with you and Hasselgren, and we're both from NVIDIA Research. The goal of this work is to create stunning-looking images at interactive rates with the help of denoising. Our renderers include motion blur, defocus blur, a large material diversity, and full global illumination. A main challenge when path tracing at interactive rates is that you can only afford to trace a few paths per pixel. One example is shown to the left, where I showed the result after 8 paths per pixel, and you can see that it's very noisy. So the task at hand here is to train a deep neural network that take these noisy input renderers and create clean looking outputs. This is an active field of research, and there has been a lot of very promising results in the last couple of years. The main idea is to take the pixel averages, the noisy samples, and also provide additional feature guides, such as the depth, textured albedo, and normals, to help the neural network to retain edges and texture detail. If you look at the texture albedo guide to the left, for example, you can see that the high-frequency wood texture is captured there. If you look at the normals, it helps the network to learn where the geometric edges are. However, if you add defocus blur, all of a sudden you have noise in these feature guides, and that complicates things. You no longer have the high frequency texture information in the albedo guide, and the geometric edges are only sharp in focus. A recent paper from Gurprit et al. Has the idea to feed the denoiser with individual samples instead of pixel averages. So you provide a radiance value and the feature guides for each sample. And the hope is that this will create even better looking outputs. This is the main inspiration for our current work, and a very interesting paper. To the left here, we see very noisy input with so-called outlier samples or fireflies, and a corresponding reference with 16,000 samples per pixel. You can see there's still noise left at 16K. In the middle, I show the output from a per pixel denoiser. And if you look closely, you can see quite a bit of blotchiness. And this is due to the outlier samples. The denoiser, as working only on pixel averages, struggles to isolate the effect of these fireflies. In contrast, the per sample denoiser can more easily isolate the fireflies and create a smoother looking denoised output. Here's a case with a significant defocus blur. So you have an out of focus foreground and in focus background. And if you look at a certain pixel, you will get a mix of samples from the blurry foreground and the background. And this is challenging for a per pixel denoiser working on averages, as there's conflicting information in each pixel. A per sample denoiser can more easily isolate the different depth layers and generate a smoother looking reconstruction. Here's the third case where you have lots of specular surfaces, motion blur, and again, large amount of outlier samples. Again, for the per pixel denoiser, we see that there's ringing around the outlier samples and some blotchiness, while the per sample denoiser reconstructs a more smoother looking result. So far, so good. But one challenge of working per sample is the significant runtime cost. If we look at highly optimized machine learning denoiser working on pixel averages, it has a runtime cost of about 7 milliseconds at full HD resolution. In contrast, the per sample denoiser from Gurprit is reported to run in about 20 seconds at the same resolution when working on input with 8 samples per pixel. Furthermore, if we look at scaling with input sample count, you can see that the per sample denoiser scales linearly with increasing sample count. And this is due to that it produces a kernel for each individual sample. And if you think about it, this is a bit unfortunate because as you increase the input sample count, the denoising problem gets easier, while the cost of a per sample network keeps increasing. So this sort of led us to the idea, can we get most of the benefits of a per sample denoising network without this increased cost? We took inspiration from a layered light field reconstruction paper that handles motion and defocus blur with the help of depth layers. If you look to the left, you have a contrived scene with a red out-of-focused fence in the foreground, a moving object moving diagonally in the scene, and a static background. To the right, we zoom in, look in a small spatial neighborhood. You can see that there's a mix of noisy foreground samples, samples from the moving object, and the background. So the obvious thing to do here is to separate these samples into depth layers. We create one layer for the foreground samples with a corresponding occupancy mask, one layer for the moving object, and one layer for the background. Once we have the layers, we can now design filters for each of the layers. So for the out-of-focus foreground, we use a large isotropic Gaussian filter. For the moving object, we use an anisotropic filter in the motion direction. For the static background, a small Gaussian isotropic filter. We then apply these filters to both the radiance and the occupancy mask to create an opacity. And we do this for all 3 layers. And finally, we do an alpha compositing to generate the denoised output. So our idea now is to learn the whole thing. So instead of manually partitioning into depth layers, we let a network freely assign samples to a couple of layers. Instead of using handcrafted filter kernels, we let a network freely design kernel weights for each pixel in each layer. We then filter each layer and composite them as before. To see if this works in practice, we designed a simple proof of concept example with a bunch of textured quads at different depths and added defocus blur. So the task at hand now is to see if we restrict the network to a small number of layers, can the network learn to partition the samples into layers and then composite them to recreate a noise-free output? Here is a visualization of the 3 layers after filtering. If we look at layer 1, you can see that it contains most of the in-focus quads, along with some of the blurry foreground quads. In layer 2, you only have blurry information from the foreground. And layer 0 has some of the blurriness of the foreground objects, but also a high frequency texture detail from the in-focus layers. This is quite interesting. Instead of doing the obvious thing of strict depth partitioning, the network has chosen to do somewhat like a depth partitioning, but also separate texture details in the different layers. To the right, I show the composited results, and this is very close to the reference. We then moved on to more complicated assets. We trained on large collections of Monte Carlo path traced scenes. To the left, I show the input samples at 8 samples per pixel in linear HDR to more clearly visualize the differences. To the right are the samples assigned to layer 0 and layer 1. It's still a noisy mess, but if you look closely, you can see that there's a lot higher variance in layer 0 than in layer 1. So it seems that the network has chosen to somehow divide the samples. Here's another scene, and again we see the same behavior. One of the layers is much more noisy than the other. Here's a third case on a scene with a large defocus blur, where again layer 0 is significantly more noisy, and the network seems to has partitioned into one easy and one hard layer. We then apply the per layer filters, and you can see after filtering the effect is much more subtle. Finally, we show the composited result and the reference to the right. You can see that it's fairly close. So it seems that the network uses the freedom to isolate samples into different layers. That can be quite powerful, we think. The network architecture is inspired from the network of Gurprit, and we use a very similar architecture in the first half of the network, here highlighted in blue. So we use input samples and corresponding features. We create sample embeddings, we average them, and run a unit to create spatial context features. And our novel contribution starts in the second half of the network, highlighted in the green box. Here, instead of producing a kernel per sample, we first use a network to partition the samples into 2 or more layers. And then within each layer, we use a network to produce kernels for the pixel in that layer. Finally, we composite the filtered layers to generate the final output. I want to point out that this process is trained end-to-end. We only compute loss at the final output and backpropagate that loss throughout the network. All steps of the architectures are learned, including the sample embeddings, which is the representation of each sample feature, the partitioning of samples into layers, and also the kernel weights for each pixel in each layer. To train our architecture, we use a large data sets. We followed the approach by Gurprit and created a random scene generator. So we use 50,000 3D models from ShapeNet, a vast collection of HDR probe, textures, many materials. We randomized more or less everything. This created a vast collection of scenes that we used to train networks. To evaluate the trained networks, we used scenes from Benedict Biddley's resources, and we moved the camera around and added defocus blur. We also included some skinned characters and some simple physics simulations to stress out interesting motion blur cases. To evaluate our networks, we compared 3 network variants in very similar settings, all trained on the exact same dataset. The first variant is entitled Pixel Gather, and this is a network that outputs a kernel per pixel, which is applied on the average pixel value. And this is a representative for most commonly used per pixel denoisers. The second variant is entitled Sample Splat. This is a network that outputs a kernel per sample. The kernel is applied per sample as a splatting operation. This variant was the best performing option in Gurprit's paper. Finally, our proposed variant called Layers uses 2 layers and a kernel per pixel per layer. If we revisit the network architecture overview, I want to point out that the left side of the network, highlighted in blue, is shared for all three networks. So we use the same unit in all three variants. The second half, highlighted in green, is different for all variants. For the per pixel network, we generate a single kernel per pixel and apply that. For the per sample network, we generate unique kernels for each sample. And for our per layer approach, as visualized here, we generate a unique kernel per pixel per layer. If we look at image quality metrics, and here I show the average values over the test set, the differences are generally quite small. The relative MSE goes down when we move from a per pixel denoiser to sample or layer, but in general, the differences are quite small. In terms of visual comparisons, here again, we revisit the case with significant outliers. Given the input samples, I would argue that all three denoisers do a fairly good job. Quite impressive reconstruction. But at closer inspection, you can see that the per pixel network struggles more with the outlier samples, and the reconstruction is more blotchy. For the defocus blur case, the added freedom from the per sample and layered networks to separate samples produces more visually pleasing reconstruction. Here's another defocus blur case with challenging visibility. And again, the per pixel network struggles to reconstruct the background in this case, some artifacts, while the reconstructed results from the per sample and layered networks are more smooth. Here's the classroom scene, and we see the same behavior with slightly more blotchy reconstruction in the per pixel denoiser. And finally, here's the case with motion blur, lots of specular surfaces, and outlier samples. And again, we see some blotchiness around outlier samples, while the per sample and layered approach are more smooth. In terms of runtime performance, and here I show the cost in number of fuse multiply adds for a full HD frame reported in billions. In the bottom, we see the pixel gather network, which has a fixed low cost. Our layered approach scales slightly with increased input sample count as we do some work per sample. In contrast, the sample splat network has to produce a kernel for each individual sample, so the cost scales linearly with increased input sample count. I mentioned in the beginning that our final goal was interactive denoising. So we designed a scaled-down variant that exploits a smaller unit and so-called hierarchical kernel prediction that runs in about 40 milliseconds at 1080p. So it's not real-time, still interactive, but we're getting there. For more detail about this network, please refer to the paper. So to conclude, layer denoising retains most of the quality of per sample denoising architecture at a fraction of the cost. In our evaluation, the benefits of denoising per sample instead of per pixel were quite subtle. In general, per pixel denoisers today are impressively good. The main benefit we saw was more robust handling of fireflies, and 2 layers seem sufficient in practice to handle this outlier separation. The differences between per sample and per pixel architectures are smaller than reported by Garb et al. I'd like to point out that we use a slightly smaller architecture and reduced number of per sample features. Our final goal was interactive denoising, so we used 20 instead of the 74 floats per sample as suggested in the original paper. For future work, we would like to look into a temporally stable denoiser. We think a layered approach can be beneficial when handling disocclusion artifacts. Thank you very much.
Thank you very much. So everybody, if you have questions, please step up to the mic and state your name and affiliation. Sorry, that's wrong. Please go to the Rocket chat channel that's for this paper, and please ask your question. I see that one of you is typing a question, but in the meantime, I have a question for you, Jacob. When the title said layer rendering, I was expecting the layers to have some sort of geometric meaning, but as you showed in the talk, they're layers, but they're not related to depth, basically.
Yeah, it's correct. I mean, when we first implemented the tests, we envisioned that pure depth layers would work quite well. But as it's a trained approach, we thought we might as well give the network freedom to partition more freely. But I should point out that we still do an alpha compositing at the end. So it's still an ordered composition in depth.
Okay. So we have a question from Nati Hoffman. He's asking what hardware was used for the quoted performance numbers, such as, for example, the 40 milliseconds for scaled down implementation.
Yeah, sorry, I should have added that to the presentation. It's stated in the paper. It's an RTX 2080 Ti, so a high-end NVIDIA GPU.
And another question from Zheng, which is, for scenes without defocus and motion blur, is it worthwhile to use the layer decomposition? Or say, does the layer denoising improve the final quality in that case?
Yeah, it's a good question. As I said in the conclusions, the main benefit we saw was in firefly removal, or to be more robust against fireflies. But it comes at a cost. So depending on the application, it might not be worth the additional runtime cost. Because as you show in the image quality metrics, the differences are very subtle and very small. So yeah, depending on your application, it might or might not be worth going on the layered or per sample approach. I mean, I was very intrigued by the per sample paper by Gurprit et al. And I really want to see how much of that approach can we sort of incorporate in a real-time scenario. And after working on the paper, I was a little bit disappointed because we envisioned larger differences.
Okay, so we have a question from Tobias Richel, which is related to the previous one, which is how about just removing fireflies naively? Yep. Say just the 1% of brightest pixels in the learning loop. This is, of course.
Yep, good question. And that was, of course, the first thing we tried. And the challenging thing is that networks, depending on which loss you use, are quite sensitive to energy preservation. So if you remove fireflies naively, that is sort of remove energy from the process, it's a more challenging training scenario. But what we should do is test one of the state-of-the-art firefly removal filters. I think Tobias is on one of those papers. But at the same time, I would argue that a layered approach is a pretty nice way of getting firefly removal as part of the denoising process. Because what we see in practice is that the network actually isolates most fireflies in one of the layers.
Okay. So one question was from Simon Fenney was about the energy cost for each frame, if you have it.
I'm not sure what he means by energy cost. Is that the how many watts that would take?
So yes.
Yeah. If that's the question, it's quite expensive because I mean it's a big network. It's a large unit. So yeah. Okay. Yeah, we don't have firm energy numbers, but I mean it takes 40 milliseconds on a high-end GPU, and that's running. It's heavily utilizing the tensor cores on that GPU, so it's expensive.
Okay, we have 3 questions left, but also my negative 1 minute left in the Q&A session. So I'm going to keep one of the questions for the end of the third paper, because it's basically how do you compare your paper with the other work presented. So I think it's best to have this after we've had all the presentation on denoising. And that was a question by Ravi Ramamurthy. I hope you'll pardon me, Ravi. The other question by Tom Giluli: did you visualize and find any meaningful structure in the filters that your network outputs?
It's pretty hard because we design a unique filter kernel for each pixel in each layer. So no, we didn't visualize them individually because it's
okay.
It's just so many kernels. But it's an interesting idea. We should go in and look at a few pixels.
Okay, and last question by Nati Hoffman. Would scaling to multi-GPU via simple screen splitting work, or would there be artifacts between the screen regions?
It would work. I think, well, I haven't tried it, but you need a guard band.
Okay.
So you lose a little bit of performance, but yeah, no, it should work just fine. I mean, we train on small tiles, on crops, and we then run inference at full HD resolution. So yeah, no, this should work without any problem.
All right, so now you and the author of the other paper can prepare for the question I will ask at the end of the session, and we can move to the next paper of this session by Lorenzo Tessari, Johannes Hanika, Carsten Dachsbacher, and Marc Droske. Lorenzo, Johannes, and Carsten are working with the Karlsruhe Institute of Technology. And Lorenzo, Johannes, and Marc are also working with Weta Digital. Keep in mind, it's currently 2 a.m. in New Zealand, so I do hope those of you who are working at Weta Digital are not in New Zealand right now. And so keep in mind, you can ask your question on Rock and Chat while the video is running. You don't have to wait for the end of the session, and I can prepare my questions, during that. With that, over to you for the video.
Hi everybody, welcome to our presentation. We're gonna show you how to have a nice motion blurred highlights in less time than before. But before starting, let's have a look at some motivational example. Here you can see the bad guy using a fearsome motion blurred rough metal quintuple chain. The combat scene continues with fast pacing action, slow-mo spins, and camera rotations, all while the light filters from some holes in the ceiling, painting nice highlights. Shots like this can be challenging, especially when lit by small light sources. Unfortunately, in production, this is quite common, and every compute cycle spared is a happy one. Let's see what you can do now about this. First things first, let's reduce the complexity from a production asset to something we can handle more easily. This is a rotating gear ball taken from the Shader Toy website. You can find the link on our paper or at the end of this presentation. So far, it's not too demanding and it can be rendered in a reasonable amount of time. But as you've seen already, in movie production there's no time to rest and everything moves very fast. Camera, geometry, and highlights as well. Let's focus on those for a moment. As you can see, sampling the highlights is hard, especially where the geometric normal under the pixel footprint changes a lot. This can be seen, for example, in the left part of the image, as the chances of reflecting towards the light are really small. Now you take this situation into an action movie and things get really messy. The electric objects moving everywhere and never enough time to have those 30,000 samples per pixel where you want to. Okay, this is difficult, but how much? Here you can see a motion blurred shot of the gears. Even for this easy setup with only direct lighting, it takes 10,000 samples per pixel before converging to something you will want to release. Since brute force is not always an option, Let's see if there's already something we can use to help. Luckily, someone already came up with a very good idea. Increase the roughness of your BSDF, considering the curvature of your geometry under the pixel footprint. This procedure is minimally invasive and helps in sampling these highlights. More recently, this technique got a couple of nice improvements. The filtering is done in world space, and the error introduced at gazing angles has been taken care of. Unfortunately, this is not enough for our use case. While accounting for curvature definitely improves our chances of sampling the glints, it is still not enough and can lead to blurred edges. This is due to the fact that motion is inherently anisotropic, so both time and anisotropy have to come into play. Nevertheless, this is a promising start, so let's see how those methods work. We will build on them. Here's how our presentation will continue. First, we'll see how highlights are formed. Then we will delve into previous work for the spatial domain, and after that we'll introduce our work on filtering in time domain instead. We will then discuss our analysis of the filtered microfacet and show practical results of our approach. Okay, so where does a highlight exactly come from? Let's start from a simple example. The light coming from all directions to the point P is scattered towards the camera. Since the amount of energy that the point receives is not changing with the camera position, it's safe to assume that the highlight depends on the scattering coefficient of our BSDF. Here you can see the formulation of a classical microfacet BSDF. It models a microscopic specular facet distribution on a rough surface. Depending on its starting roughness, it can range from diffuse to perfectly specular. Let's look at the terms in the equation to see where the intensity spikes come from. F is the Fresnel coefficient that tells us how much light is reflected and how much light is refracted. G instead is the masking shadowing term, accounting for the amount of occluded and self-occluded microfacets. Both of them are bounded between 0 and 1. Lastly, D is the normal distribution function that we will filter later. It is responsible to give the density of specular microfacets that share the same normal as the Hall vector, obtained from incoming and outgoing direction. This term can change rapidly and drastically, especially when the roughness of the microfacet is very low. Okay, now we have seen that the change of the Hall vector has a drastic impact on the amount of light scattered, and we would like to filter this distribution to better handle the specular aliasing. But what to do if we don't have the Hall vector ready at hand? There are cases where lights are not known at a certain stage of the pipeline, or you want to be independent from any light sampling strategy. Think, for example, of the third rendering. A common approximation in this case is to assume that both camera and light are very far in world space relatively to the pixel footprint. Like the light of the sun, minor changes in omega are negligible, and the Hall vector is thus affected only when its tangent frame rotates. This brings us to another useful approximation. Since our use case concerns highly glossy materials, which have very low roughness values, we treat every interaction event as a perfectly specular reflection. This is a conservative estimation that holds well up to reasonable high roughness. In turn, we can assume that the Hall vector is equal to the normal, which lets us be independent from any light sampling technique, especially when light sources are not known in advance or specific sets of techniques are used only when explicitly needed. Our next step starts from the camera. Through ray differentials, we can obtain the normals at position P0 and P1 of the pixel footprint F. This gives us the derivative of normal change that we want to map in slope space to filter our distribution. Another option is to project the derivative in the tangent space given by the mapping, in order to avoid artifacts at gazing angles. This is due to the fact that the first-order approximation error is potentially unbounded in slope space. Now that we have our derivatives, it's time to filter some distribution. Here we map our starting roughness to a Beckmann. Being a Gaussian in nature, it is an easy pick when it comes to convolve with another Gaussian kernel. From the derivatives, we then construct a 2x2 covariance matrix and use it to filter our Beckmann by simply summing up the two covariances. The result is our final combined distribution sigma conv. Even the first order derivative and the fact that the mapping from spherical to slope domain is not preserving the Gaussian shape, this results in an approximation. For low to moderate roughness, as in this case, it works well. Now that everything is set, we have two options. Either we consider the new distribution as is and evaluate the full covariance matrix in our microfacet model, or we can directly extract from it the new roughness value. For the latter, if the Gaussian is not axis-aligned or the filter kernel isotropic, it is necessary to extract the new roughness and the tangent frame through a singular value decomposition. As we've seen, accounting for curvature under the pixel footprint can be very helpful. But what happens when you take time into account? For a motion blurred shot, the geometry subtended by the pixel changes during the shutter interval, or dually, the pixel footprint extends in word space. If sampling highlights was hard before, now it's even worse. The spread requires a higher number of samples as they start to be far apart from each other, as can be seen in the rightmost rectangle. This can give some intuition of how the previous techniques are not sufficient to solve this problem. Ideally, we would like to cover the same amount of space by elongating also our samples, retaining the good properties seen so far. A new kernel that elongates in the same direction of the moving object seems a good idea to try out. Similarly as before, we trace a ray differential but in time. The formulation that we derive in the paper is a more general version of the classic ray differential. In our version, the derivative of the intersection distance does not only depend on space, but on time as well, given our needs. This restricts its use to unidirectional methods, as any other ray differential technique, but serves well enough for our cause. Please check the paper for the details on our derivation. Continuing on, the normal change under the elongator pixel footprint gives us the derivative that we were looking for. It encapsulates both the direction and the magnitude of the motion. This is exactly what we were searching for and allows us to have a kernel that follows the object's motion. The new covariance is simply the outer product of the derivative with itself, or alternatively, the new roughness and tangent frame can be extracted directly from it. Since the variation is monodimensional, the roughness on the minor axis is set to 0, or in case of a perfectly specular material, to a very small value. Another difference compared to the previous work is the evaluation of the G-term. While filtering the distribution that has a spatial extent modifies also the shadowing and masking of it, in our case we account only for a change in time. This means that the shadowing and masking does not differ between two different time extents, and thus the new distribution has to be evaluated only for D, keeping the G term that comes from the initial BSDF as it was. So, how does it look in practice? Normally, it will be quite hard to visualize since everything will be in motion and blurred to its speed. On the other hand, if it's not moving, then our derivatives are 0, since the normal doesn't change over time. So, here's the trick. On the left, we have the droplets rendered at a fixed time, and on the right, our filtering applied as if they were moving. As you can see, the bright spots are nicely resolved, following the motion of the particles. As we were mentioning before, combining micro and macro surfaces or convolving them is not exactly the same thing. Let's have a look at the explicit formulation and at our approximation. For the microsurface in green, we have our microfacet BSDF that we encountered before. The macro in red is represented by our filter that extends over the spherical domain. In the combined version, we need to integrate over all possible half vectors m of the macro surface, with a change of variables to move from the macro to the micro surface. This is in fact impractical in rendering, and it will be too expensive to evaluate exactly. But looking at how the equation extends itself, we can notice that it has the structure of a convolution between the two distributions. Using a Beckmann for both macro and micro, since a convolution within Gaussians is closed, seems the perfect choice. Unfortunately, the mapping from spherical to slope domain does not fully retain this property, but for a low to moderate roughness is a good approximation. We can see this formulation in the second equation. What we were suggesting before is that our microfacet does not differ between two different time extents. So let's see exactly how this approximation behaves when considering the full covariance or only the base one for the G term. In our experiment, we have a fixed outgoing direction, and the macro surface in red is anisotropic non-axis aligned with 0.3 roughness along the major axis and a very small amount 0.015 on the minor. For the micro instead, we use an isotropic distribution in green and a low roughness value. This is the case where the G term evaluates both macro and micro, whose singular curves differ, but both combined and convolved version align well. Here instead we tested the G term only on the micro. This is in fact needed to assure that our assumption for the temporal domain does not break under this approximation. Back to full G term evaluation. This time we move the micro roughness to a moderately high value of 0.5, as can be seen from the green curve. This is an example when the convolution approximation starts to show its limitations, but luckily for us, it's far away from our intended use case. Unsurprisingly, the same applies when we try again to evaluate our G term only on the micro, set to the same value as before. Here we can see a sphere moving back to front, leaving a highlight curved trail due to the change of the view angle during the motion. The movement itself instead is straight. If we use our method as is, the stretching of the kernel following the path that the sphere is taking is linear, and this leads to the sparkles that you can see in the leftmost bottom image. This comes from the fact that we use a first-order derivative, resulting in a linearization error when mapped to the Beckmann distribution. To be correct, we will need a higher order that will in turn change the distribution into a banana shape, as the correct NDF is curved on the sphere. You could see a visualization of this in the bottom right image. Another element that we cannot factor in is visibility. While our filter accounts for the motion of the particles, different velocities and trajectories can lead to self-shadowing. This is usually not very noticeable, especially if the time delta is chosen properly, but high speeds can still lead to some overblur. And now the results section. As a start, we're going to focus on the highlights of these two scenes. We already saw the first at the start of the presentation, so the new challenger is, as maybe someone expected, a chain. Both scenes were taken from Shader Toy, links on the paper or at the last slide. This scene is a very good testbed for motion in all directions. Each gear has its own axis of rotation, and the fast-changing normals make it quite hard to resolve highlights. Given the premises, it's no surprise that a spatially anisotropic filtering that focuses on curvature does not help, but at least keeps the highlight sharp. On the other hand, its isotropic version manages to get some of the motion, causing as well overblur both on the side of the highlight and on the dents of the gear. Our technique instead does not suffer from this side effect, and increasing the roughness only along the motion vector results in a sharper and more converged image. Here we can see the reason behind the previous results. This is a false color image where we mapped the roughness values in the red and green channel for the major and the minor axes respectively. The spatial anisotropic filtering increases the roughness along the edges, mostly in one direction, so if it doesn't align with the motion, the sample is simply wasted. The isotropic version does the same in all directions and results in a general overblur. Our method doesn't touch any part where its normal stands still during the motion, focusing on the moving gears only. This is a simpler scene for the other spatial techniques. The motion is axis aligned towards the top and has enough curvature to align the filter with the movement vector. One important factor is that the roughening needs to scale with the object velocity. So while all techniques do not particularly struggle with this setting, they stay behind in convergence speed. Same as before, our technique increases the roughness along the motion in a significant way compared to the other two, thus explaining the quicker convergence. To conclude, here's a short summary of our talk. We showed a new method that is useful for rendering motion blurred highlights, moving previous work from the spatial domain to the temporal one. As such, shares with them the same approximations for the first-order derivative and the convolution. On the brighter side, being a different domain, it's orthogonal and in principle can be used in conjunction with previous techniques. Lastly, it's independent from the light sampling, increasing its flexibility to multiple contexts. A huge thanks to our amazing colleagues at Weta that helped and support us, and a thank you to Luca and Joe for supporting this project. By the way, they're hiring. Thank you for your attention during our talk. Now we're ready to take your questions.
Thank you very much for this inspiring talk. As usual, if you have questions, please step to the Rocket Chat private session for the talk, and I will forward your questions to the authors. In the meantime, since there doesn't seem to be any questions in the Rocket Chat yet, I have a question. Am I correct in assuming that this currently only works with reflections on droplets, and what would you need to change to make it work with refractions through the droplets too?
Well, in this case, you will need also the indirect pass of the differential, which is still an open topic, and it's, especially in the temporal domain, not a very easy way to do, nor even thinking what is the right way to do.
I don't know. It's a matter of computing the differential. Yes, we didn't do it, but
actually, I should have asked the question: is it a problem? Do you see issues related to refraction?
I don't think. I mean, usually you have the problem that you have a much reduced sample count through refraction, because at least half of your samples reflect when they shouldn't. At least in some places. So it reduces the sample count, the differentials. That would be a matter of just figuring out the equations, transport it to where you need it in half vector space. And there's another question of how would you split up roughness? Like, as opposed to the previous works, we don't get a kernel in image space and blur it there. We tried that as well, but it leads to overblur. So we split the kernel in half vector space at the vertices. So if you have a longer path, you have a choice, right? Where do you add the roughness? You just have maybe contradicting motion vectors, and you want to split them at a certain set of vertices to receive the overall correct blur. So there's open questions to figure out, but it's certainly on our radar. Like, to be able to do this in path space, we are going down this route.
Okay.
That answers the question.
Yes, it does. It does. I mean, wasn't expecting a definite answer yet. I have another question while the other people are preparing their questions. I'm not sure I've seen the overblur on the slide with visibility. If that's possible to go back to the slide.
Oh.
The visibility occlusion, like the occlusion error?
Yeah, you mentioned there was some other blur, but I'm not sure.
I mean, figure 9 in the paper. I don't know how I can share my screen in this Zoom thing. I don't know. I can go back and show you a picture.
Yeah, I can.
If you look closely, I'll just explain what you're supposed to see, and you can go back and.
Okay, so yeah, I'm looking at figure 9 now.
Okay, to the left, you see top left corner some high frequency edges. Looks like occlusion, shadowing of stuff that is not moving.
Oh,
you see that? Okay. It's a little blurred on the right hand side.
Oh. Okay, got it. Yeah, okay. I see. And okay, so we have a question from Tobias Rachel. Could visibility be addressed by layering? So put droplets eventually occluding each other on individual layers, blur them independently, compose again.
Probably yes, but then you will need really a lot of layers, I guess, in this case. So I'm not sure if that's feasible.
So the thing is, we're not blurring the image, right? I did experiment before we did this work with splitting up stuff in layers with no network, but with a firefly detector and blurring that per sample or per pixel. But that's an image space operation in the end. I mean, samples or pixels, you do it in image space. And now we're doing it on the BSDF. So that means we don't over blur geometry. Like if a droplet flies until here, we never blur outside of that interval. Right, so I don't know how I would combine layers with half vector space blurring. I have to think about this, but yeah, I mean, the layers are certainly interesting.
Okay, and so I have one last question. Tobias is writing. I have one last question. It's if I read the paper correctly, this works best with implicit surfaces because you need local derivatives.
Mm-hmm. I mean, potentially you could take the normal in 2 different times close to each other and then use just a finite difference.
We're mostly interested in implicits because simulation.
That's based on the problem, right?
Exactly. It works if you have triangle meshes with vertex normals and you get your differentials from there as well. But yeah, the use case was mostly implicits, and also we could get two nice scenes for cheap. So yeah, that was good.
Okay, thank you very much for those great questions. I don't see any other questions in the chat, so I suggest we move to the third paper of the session. So this paper is authored by Xiaoxu Meng, Zheng, Amitabh Varshney, Gurprit, Singh, and Matthias Zwicker. Xiaoxu, Xuan, Amitabh, and Matthias are with the University of Maryland College Park. And at the same time, Quan and Gurprit are with the Max Planck Institute for Informatics. And the talk will be on real-time Monte Carlo denoising with the neural bilateral grid.
Good morning and good afternoon. Today I'm going to present real-time Monte Carlo denoising with the neural bilateral grid. Path tracing is a commonly used Monte Carlo method of rendering photorealistic images. Path tracing naturally simulates many effects that have to be specifically added to other methods, such as soft shadows and indirect lighting. However, in order to get high-quality images from path tracing, typically you need hundreds to thousands of samples to avoid noisy artifacts. In the case of real-time rendering, the realistic budget for us is approximately only 1 to 2 samples per pixel, which is extremely insufficient to get something clear. People have been fighting up with the noise over the recent years, and our weapon is denoiser. Many state-of-the-art denoising methods have been recently developed over the past few years. Here are some examples of the offline denoisers, which pair up with a renderer to clean up the image after the rendering. Recently, many denoising approaches with fast filtering have also been developed for real-time applications. To meet the real-time requirements, we started to investigate a denoiser designed for extremely low sample count, which is 1 SPP, and we target at denoising frame rate greater than 60 FPS with high denoising quality. These requirements remind us of an old friend who is a master in edge-aware image processing with super high speed, and his name is Bilateral grade. Bilateral grade is a 3D representation of 2D data. By the operation of grade creation, we lift image processing into a higher dimensional space. We can design algorithms that naturally respect strong edges in an image. By the operation of grade slicing, we can map the filtered pixels from the bilateral grade to the image. Bilateral grade has demonstrated efficiency in edge-aware painting, tone mapping, recoloring, and style transfer. The motivation for using bilateral grade in Monte Carlo denoising is to avoid the explicit computation of per-pixel weights for large filter kernels, which requires deep networks. Instead, we learn to embed the data into a higher dimensional space, which allows us to achieve high-quality denoising with a fast, spatially uniform filter. In addition, we can use very efficient network that learns the embedding. In this part, we introduce the overall multi-scale architecture of our neural bilateral denoiser. To make it easier, I will start with the single-scale architecture. There are 5 stages in this pipeline. The first stage is pre-processing. Firstly, we factor out the albedo from the radiance and conduct pre-temporal accumulation, so the neural network can focus on the noisy patterns in smooth irradiance data. The second stage is guide prediction. We predict a guide image for splatting noisy irradiance data into the bilateral grade. The third step is grade construction. We construct the bilateral grade by leveraging the corresponding value in the guide image to instruct the placement of pixels from the noisy data to the bilateral grade. In the next step, we reconstruct a denoised image by slicing the bilateral grade. This is the semantically symmetrical procedure to the bilateral grade construction. And finally, we remodulate the albedo back to the denoised image to get the final result. This is a 5-stage pipeline of the single-grade architecture. To achieve better denoising effect, we propose the multi-scale grade approach using 3 grades at different resolutions. For each scale, we generate a separate guide image from the guide night and use it to instruct the construction of the bilateral grade individually. And we also predict 3 pixel-wise weight maps. We compute the weighted composition of the outputs sliced from the grades to form the final radiance. The key idea behind our approach is that for a suitable guide, we can use very simple and fast convolution operation to finish the denoising. Now let's take a look at the detail of different stages. I will start with grade construction and slicing, then I will introduce the multi-scale design and the guide prediction. We define 3 sampling rates for the 3 axes of the grade. For the image with size of W and H, we can calculate the resolution of the grade. For each grade cell with coordinate of X, Y, and Z, we can calculate the coordinates of the splatting center. We can also calculate the splatting region in the image. The grade value is the weighted sum of all the pixels in the splatting region. We use a tent filter to calculate the weight for each pair of U and X, and each pair of V and Y, and the depth coordinate of pixel UV in the bilateral grade is given by the guide. We can still calculate the weight using the tent filter. If the weight is 0, the pixel will not be mapped to the grade cell. The splitting weight is a product of all the weights for the x, y, and z axis, and we can calculate the value of the grid cell by taking the weighted sum. Here is a visualization of the construction of the bilateral grid with depth equals 4. The 1 SPP radius and the guide image are shown on the left. They are used as the input of the grid construction block. The right side shows the scan of the bilateral grid and the 3D bilateral grid. And here is a bilateral grid with depth equals 8. And here is also the grid with depth equals 8, but we further squeeze the width and the height. By choosing the proper grid resolution, we expect that the neural network can learn to place the noisy radiance data in a bilateral grid in an optimal way. We reconstruct a denoised image by slicing the bilateral grid. This is a semantically symmetrical procedure to the bilateral grid construction. Now let's think about the key factors for the denoiser. The first one is grid resolution. If the grid is too large, the irradiance is sparsely distributed in the bilateral grid and the filter is not powerful enough. While if the grid is too small, the data will be squeezed and the denoised image will be over-blurry. Moreover, the requirement for the denoising power might be pixel-wise. Therefore, we introduce the design of the multi-scale grid. Given the input noisy frame, we build a 3-scale pyramid of bilateral grids by choosing different sampling rates. Another key factor for the denoiser is a guide image. Instead of manually crafting a guide, we propose to use a neural network to learn to place the noisy irradiance data into the bilateral grid in an optimal way. For denoising one SPP input at real-time speed, we use a 2-layer convolutional neural network as shown on the left. For denoising 64 SPP inputs that are not produced in real time, we utilize a 7-layer convolutional neural network that contains a 5-layer dense block as shown on the right. For each layer in the block, we concatenate their feature maps to its following layers. In both architecture, we set the 2D size of convolution as 5 by 5. We employ ReLU activation for the layers before the last one, while we use sigmoid activation for the last layer, so the range of the output is from 0 to 1. Now let's talk about the experiment setup. I will talk about the dataset preparation, training and testing setups, and the implementation. We use 2 datasets in our experiments. We firstly adopt an existing 1 SPP dataset from the previous work, which contains 6 scenes with 60 consecutive frames for each one. In addition, we build a new 64 SPP dataset of publicly available tungsten scenes. Both datasets contain the HDR radiance as well as auxiliary features including albedo, normal, and depth. For both datasets, we hold out frames of one scene as a test set, and we use the remaining images of other scenes for training. In the training stage, we use image patches at a resolution of 128 by 128. In the testing stage, we use the original image with a resolution of 1280 by 720. Our denoiser is implemented in TensorFlow. A typical training time for one test scene using 100 epochs is about 14 hours on NVIDIA RTX 2080 GPU. Now let's talk about the results. I will introduce the evaluation methods and the error metrics, followed by the quality comparison and ablation studies. Since our approach aims at real-time denoising, we mainly focus on comparisons on existing real-time denoising approaches. We also include a comparison with an offline denoiser, N4. For BMFR, SVGF, and N4, we use the implementations provided by their authors. The original kernel prediction denoiser is designed for the offline denoising and requires several seconds to process a single 720p frame. Similar to our multi-scale design, we have adapted the multi-resolution kernel prediction denoiser, which decreases the runtime of a basic kernel prediction architecture to the order of tens of milliseconds. Hence, it is an important comparison point for real-time denoising. Details of the architecture of MRKP can be found in the supplementary material. For fair comparison, we train MRKP with the same loss and the same split of data as our approach. Also, we perform the same temporal filtering and albedo demodulation as in our approach. We will show the evaluation with PSNR and SSIM here. We have included other evaluation metrics and error maps in the supplemental material. Firstly, we show the performance of our denoiser on the 1SPP dataset. It can be observed that our method generally provides higher PSNR and higher SSIM. MRKP with 5-layer also shows good performance. Now we show the denoising result of Singh classroom. Here is the 1SPP radiance. And here is the denoised image. And here is a reference. Our method performs well at preserving the details. Now we show the denoising of 1SPP Sponza glossy. Here is the original 1SPP Sponza glossy. And here is the denoised image. And here is a reference. Our method performs well at preserving the detail, such as the highlights on the wall and the face of the line. I will show the video of the denoised frames for two 1SPP scenes. Good morning and good afternoon. Today I'm going to present real-time Monte Carlo denoising with a neural bilateral grid. Path tracing is a commonly used Monte Carlo method of rendering photorealistic images. Path tracing naturally simulates many effects that have to be specifically added to other methods, such as soft shadows and indirect lighting. However, in order to get high-quality images from path tracing, typically you need hundreds to thousands of samples to avoid noisy artifacts. In the case of real-time rendering, the realistic budget for us is approximately only 1 to 2 samples per pixel, which is extremely insufficient to get something clear. People have been fighting up with the noise over the recent years, and our weapon is denoiser. Many state-of-the-art denoising methods have been recently developed over the past few years. Now let's see the denoising of the 64 SPP scenes. Our method performs well at preserving details. In the living room scene, we can successfully recover the glass on the ceiling and the branches in the vase. In the kitchen scene, only ours and ONND can successfully recover the text of bread. I will show the video of the denoised frames for 164 SPP scene. Good morning and good afternoon. Today I'm going to present real-time Monte Carlo denoising with a neural bilateral grid. Path tracing is a commonly used Monte Carlo method of rendering photorealistic images. Path tracing naturally simulates many effects that have to be specifically added to other methods, such as soft shadows and indirect. It can be observed that our method provides high PSNR and SSIM. To measure the time cost of denoising, we apply all the denoisers on the same test set. The mean time cost to denoise a frame is averaged over all the 1SPP test frames. Our denoiser using a 2-layer GetNight and a 3-scale bilateral grades can run at a real-time performance which reaches 61 frames per second. The scatter plot of PSNR and timing shows that our denoiser performs the best in terms of PSNR. Meanwhile, our denoiser stands a comparable position for speed. To analyze the impact of training a neural network to obtain optimized guide images, we compare our approach to a baseline where the guide image is simply the arithmetic mean of the auxiliary features. The baseline shows apparent artifacts around edges because it cannot guide a correct splitting of the noisy radiance. We also investigated the effect of removing albedo from the noisy radiance input. As shown in the insets, our denoiser successfully preserves the details from albedo by performing albedo demodulation. Specular light paths are notoriously difficult to sample, thus often leading to extreme noise. In this scenario, features such as albedo textures also provide little useful information to the denoiser. As shown in the figure, all the denoisers fail at reconstructing the glass vase. Since none of the datasets include scenes with depth of field, motion blur, or volumetric media, our denoiser may yield poor performance or give artifacts on such scenes with unseen effects. This problem can only currently be mitigated by increasing the generality of training scenes. To summarize, we propose a novel and practical deep learning approach to robustly denoise Monte Carlo renderings as low as 1 SPP. Our approach allows end-to-end training, and the experiments have demonstrated better denoising quality than existing methods. Thank you for watching.
Thank you very much for this awesome talk, even though there was an interesting glitch with the embedded videos. Sorry for that, guys. That's what Direct is for. Let me again ask you to go to the Rocket chat and state your questions here, and I'll forward them to the authors. I should also mention that the authors are available on the Rocket chat after the talk. And if you go back actually to the previous paper, you can see a very interesting discussion between Johannes, Hanika, and Tosia at Zwicker about a question that was started by Tosia, and that's a really awesome discussion that I suggest you all go read, but after your questions for this paper. So we have one question from YouTube, which is, I wonder how it works with the permutohedral lattice.
So we have not tested with a permutohedral lattice. I also wonder how it performs. If you are interested, we have open sourced our code and dataset, and if you are interested, you can download it and make a test, I guess.
So actually, yes, Tsumauli has a follow-up to that question. How does this compare to other more traditional edge-aware filters that do not incorporate neural networks, such as the adaptive manifolds?
So we have not compared with all of the methods. So it's also, perhaps we can make further tests with other methods, but not in our current version.
Okay, thank you. And a question from Nati Hoffman. Albedo demodulation helps preserve high frequency detail in the albedo. But what about other types of high frequency details, such as in normal maps or specular roughness maps and so on?
Okay. Actually, we have tried to exclude some features. So if we don't exclude the depths, we might mess up with some layers which are of the same normal direction but have different depths. For example, we have two walls with different depths. If we don't include the depth feature, we will mess up with the two layers. So I think all of the four features we are using are helpful. Yeah.
Thank you. And a question by Jan Novak. Do you think it is worth considering neural nets also for predicting filters used during the bilateral grid creation? Because currently you use a tent filter here.
So I mean, so it's considering about directly. So
I think he's referring to the bilateral grid creation, which is the only place where you don't use a neural net.
If we sorry, can you please repeat the question?
The question was, do you think it's worth considering neural nets also for predicting filters used during the bilateral grid creation?
Okay, so yes, that's an interesting direction. So I think we can perhaps try some approach, which like we can try, because currently we are using a spatially uniform filter. We can perhaps try to use the neural network to predict the filter size of the bilateral grid instead of using a spatially uniform filter. But I guess it will increase the time budget because the timing budget for us is very limited, and predicting a kernel for the neural bilateral grid will increase the timing cost a lot, because predicting the per pixel weight is very expensive.
Oh, yeah. So Eric Patterson is asking, I may have missed it, but what type scene and complexity were you reaching 61 frames per second?
Yes, we are not performing the best in the 64 SPP. We have found some errors in the I think it's because other methods are also performing well, and because our filter is spatially uniform, and our method cannot deal with some of the cases where when we need very large filter kernels, and that's why we have suffered some quality degrade.
Okay, and now let's have something challenging. We're trying to go back to the author of the first paper and have both authors of the first and third paper answer Ravi Ramamurthy's question, which was, how do both papers compare with each other, basically?
I think this question is very interesting. I think the paper with layered denoising can deal with some problem like motion blur or depth of field, but we have not included this kind of training data in our data set. So I don't think our network can deal with this kind of cases. I think, yeah, but I would like to include more training data in our data sets so to see what happens.
Yeah, I could perhaps add, first I want to say that the neural bilateral grid paper is really interesting, and you made a great job of comparing a lot of different denoisers. I think the multi-resolution kernel prediction network that you use is quite similar to the pixel gatherer network that we compare against in our paper. So I expect the quality to be quite similar. But I think our goals are quite different. I mean, if I understand your paper correctly, it performs best at 1 sample per pixel, and mainly diffuse scenes with when you do albedo demodulation. And we have focused more on sort of 8 sample per pixel input with motion and defocus blur. But I think the neural bilateral grid is super interesting because it's extremely fast. So I think for game like denoising, it's something that we should look closer into.
Yeah, and also the layered denoising also tries to remove the firefly artifacts. And in our method, in our paper, we show an approach in which we just remove the very bright fireflies by using some energy suppression. But if we compress the energy of the image, we have experienced some decreasing of PSNR, and I think we can apply some better firefly removal methods.
I'm curious, what's the spatial resolution of the highest bilateral grid? Are you the highest level? Is that you have a grid cell per pixel, or is it downsampled?
So we have downsampled with downsample rate equals 4. So for our 720p image, the maximum grid resolution is 720 by 160.
Okay, thanks.
Thank you very much for this great presentation and answers. Keep in mind you can continue the discussion with the authors on the Rocket chat channels, but I think it's now time to move to the second session of the first day of EGSR.